Magandang umaga, tanghali, hapon o gabi sa inyong lahat. Ngayon ay pag-uusapan natin ang iba't ibang statements ng second law of thermodynamics. By the end of this video, matututunan ninyo ang mga key concepts tungkol sa second law na tulad na lang ng spontaneous processes, irreversibilities at entropy. Mauunawaan din ninyo ang iba't ibang written form ng second law of thermodynamics tulad na lang ng entropy statement, Clausius statement, at Kelvin-Planck statement. Finally, using the definition of the Kelvin temperature scale, we will quantify the maximum performance of a thermodynamic cycle given the relevant temperature values. Simulan natin ang diskusyon sa tinatawag nating spontaneous process. By definition, a process is said to be spontaneous if they can occur on their own kahit na walang presensya ng energy input mula sa isang external source. For example, ang isang body na ang overall temperature niya ay mas mataas kaysa sa temperature ng kanyang environment. We can observe that heat will transfer from the body to its environment over time hanggang sa magkaroon ng thermal equilibrium between the environment and the body. Eventually, magiging parehas lang ang kanilang temperatures. Take note that this process will occur kahit na wala tayong other intervention with the body. Isa pang halimbawa ng spontaneous process ay ang highly pressurized air sa isang container at matapos nating buksan ng container, alam naman nating kusang lalabas ang hangin mula dito papunta sa environment. That is to reiterate na ang pressure sa loob ng container ay dapat mas mataas kaysa sa environment pressure. These two processes are spontaneous. Consider the amount of energy transferred by the hot body at Ti to the environment at T0 until the body reaches a temperature of T0. The amount of heat transfer associated with this process is given by m times c times the quantity of Ti minus T0. Also, i-consider din natin ang reverse process ng process na ito. So, let's say we have a cold body at T0 na papainitin natin hanggang umabot ang kanyang temperature sa temperature na Ti. Technically, ang magnitude ng energy for these processes to happen ay parehas lang in both cases. But have you ever noticed that the first process naturally occurs while the second process does not? It is because spontaneity is a vital concept in thermodynamics. Ang pinaka-limitation ng first law of thermodynamics ay sinasabi lang niya na energy is neither created nor destroyed in a process. Pero wala siyang sinasabi patungkol sa direction ng process. That is, even though sinasabi ng first law of thermodynamics na ang energy associated with process A ay parehas lang sa energy associated with process B, hindi niya masasabi kung maaari bang mangyari ang dalawang processes na ito. This limitation of the first law is actually complemented by the second law of thermodynamics. Sa madaling salita, ang second law of thermodynamics ang magsasabi kung posible bang mangyari ang mga thermodynamic processes, provided that these were already in accordance to the first law. Isa pang mahalagang konsepto na kailangan nating i-define ay ang irreversible process. Kapag sinabi nating irreversible process, these are the processes na may irreversibility sa ating system o surroundings. In reality, all processes are irreversible. Masasabi lang natin na ang isang process ay reversible kung walang irreversibilities sa ating system at surroundings. These types of processes are fully idealized at hindi natin nakikita in reality. Now, what are the different sources of irreversibility? Una, we have friction, which is basically caused by rubbing of two surfaces na merong degree of roughness. Also, ang heat transfer because of a finite temperature difference can also be a source of irreversibility. Tulad na lang nito ng mga halimbawa natin kanina kung saan meron tayong hot body left on a cooler environment. Also, any spontaneous chemical reactions such as spontaneous combustion is also a source of irreversibility. An unrestrained expansion of fluid na highly similar sa ating pressurized air example kanina ay isa ring source ng irreversibility. Finally, ang elastic deformations at mixing are also sources of irreversibility. Take note na ang listahan ay hindi natatapos dito, pero sa konteksto ng thermodynamics, ito yung usually sources ng mga irreversibilities sa ating processes. Now, let's proceed with the different statements of the second law of thermodynamics. Gaya ng sinabi natin kanina, meron tayong tatlong most popular statements of the second law. Ang entropy statement, ang Clausius statement, at finally ang Kelvin-Planck statement. First up, we have the entropy statement. Kapag sinabi nating entropy, it is an abstract property to describe the disorder or chaos of a system. All other things being equal, kapag mas mataas ang entropy, sinasabi nating mas chaotic ang ating system. And also, as long as ang ating processes ay may irreversibilities, entropy is always produced. That being said, we can say that all real processes produce entropy. Which leads us to the entropy statement. Ang sinasabi nito ay, it is impossible for a system to operate in such a way that entropy is destroyed. Mathematically speaking, ito yung sinasabi nating for all real processes, the entropy generation Sgen or entropy production Sprod is greater than 0. If the process is ideal, then the entropy generation is just equal to 0. Next, we have the Clausius statement. The Clausius statement says that it is impossible for any system to produce a sole result so that the heat transfer flows from a cooler body to a hotter body. Sa madaling salita, ang direksyon ng heat transfer ay palaging mula sa mas mataas na temperature papunta sa mas mababang temperature, provided na walang ibang forms of energy such as work input to the system. One question can be brought into sight because of this statement. Ang mga refrigerator ba ay nagva-violate ng second law of thermodynamics? Tandaan natin na ang mga refrigerators ay nag-absorb ng heat mula sa low temperature reservoir at nagre-reject naman ng heat papunta sa high temperature reservoir. The answer to this question is no, it does not. Tandaan natin na sa ating refrigerators, the heat transfer from a cooler heat source to a hotter heat sink is not the sole mechanism happening here. In fact, tayo ay naglalagay ng power input papunta sa ating refrigerator, which is why refrigerators do not violate the Clausius statement. Next, we have the Kelvin-Planck statement. Sinasabi sa Kelvin-Planck statement na it is impossible for any system to operate in a thermodynamic cycle and deliver a net output work while receiving heat from a single thermal reservoir. Sa madaling salita, hindi pwedeng makonvert ang lahat ng heat input into useful work output. Take note that the equation Q cycle is equal to W cycle makes sense kung ang pagbabasihan lang natin ay ang first law of thermodynamics. However, because of the Kelvin-Planck statement, masasabi natin na ang ganitong systems ay hindi pwedeng ma-implement. Mathematically speaking, sinasabi ng Kelvin-Planck statement na ang value ng W cycle can only be negative or 0. It is never positive. This is because of our sign convention that the network output is positive and the network input is negative. If W cycle is 0, then we can say that the process is reversible and therefore ideal. Kapag naman ang W cycle ay less than 0, masasabi nating ang process ay irreversible and therefore it is a real process. Ngayon, i-apply natin ang Kelvin-Planck statement sa ating power cycle. Sabihin natin meron tayong heat engine na mayroong dalawang heat reservoir, ang hot reservoir at ang cold reservoir. Given that it is a heat engine and applying the first law of thermodynamics, we know that the net power output W cycle is just equal to QH minus QC. Now, we want this system to imitate the conditions of the Kelvin-Planck statement kung saan tayo ay may isang thermal reservoir. The closest thing that we can get is if we let QC be equal to 0. Gamit ang ating derived equation, masasabi nating W cycle is equal to QH, which implies that W cycle is greater than 0. However, the analytical statement of Kelvin-Planck says that W cycle can only be less than or equal to 0. So kung makikita ninyo, yung concluded statement ay contradicting with the Kelvin-Planck statement, which means that our assumption that QC is equal to 0 is false. That is by the virtue of proving by contradiction. Now, what's in it for us? Since ang QC ay isang positive number, masasabi natin ang QH ay mas malaki kaysa sa W cycle. This further means na ang efficiency ng ating heat engine ay palaging mas maliit sa 100%. Tandaan natin na sa ating efficiency formula, the numerator which is W cycle was just proven to be smaller than QH, which is why walang 100% efficient machine. Now, since QC is not equal to 0, or in other words, it is positive, masasabi din natin na in order for a machine to function, then part of the heat input must be rejected to the low temperature reservoir. Sunod ay i-apply naman natin ang Clausius statement sa heat pump or refrigerator. Sabihin natin tayo ay merong heat pump or refrigerator that absorbs heat from a cold reservoir. Also, it rejects heat at a hot reservoir, and finally, it requires work input W cycle. Bilang panimula, i-assume muna natin na ang W cycle ay equal to 0. Mula sa ating formulas for beta and gamma, pwede nating imply from this assumption na ang coefficient of performance in both cases ay infinite. Also, using the first law equation for refrigerator and heat pumps, masasabi natin ang QH ay equal lang sa QC. Now, let us pay attention to what our setup looks like if W cycle is equal to 0. Makikita natin na ang ating system ay mag-absorb ng heat from the cold reservoir at magre-reject ng heat sa hot reservoir, which is exactly yung pinagbabawal ng ating Clausius statement. This means na ang ating assumption, which is W cycle is equal to 0, together with the implications of our assumption, which is the coefficient of performance being infinite, are all incorrect. Sa madaling salita, tayo dapat ay may work input sa ating cycle at ang value ng coefficient of performance ay hindi dapat infinite. Finally, let us obtain the maximum possible performance of thermodynamic cycles by first defining the Kelvin temperature scale. Sabihin natin na meron tayong dalawang different systems undergoing a reversible power cycle here on the left at reversible refrigeration cycle here on the right. Bawat isa sa kanila ay nag-interact with their respective hot and cold reservoirs. Provided that all the processes in the cycles are reversible, the Kelvin temperature scale is defined so that QC over QH in the reversible cycle is equal to TC over TH, where both TC and TH are temperatures in Kelvin. Now, let us recall the different formulas for the efficiency in the power cycle, as well as the coefficients of performance for the refrigeration and heat pump cycles. Sinabi natin sa ating previous slide na ang mga heat transfer na ito ay reversible heat transfers. And following the line of thought na ang reversible cycles ay makakapagbigay ng most efficient performances, then we can get the maximum power efficiency and the maximum coefficients of performance as follows. Let us solve some sample problems before we end this video. A household freezer operates in a room at 20 degrees Celsius. Heat must be transferred from the cold space at a rate of 2 kilowatts to maintain its temperature at negative 30 degrees Celsius. What is the theoretically smallest power input in the motor required for operation of this freezer? So, before we officially begin our calculations, i-drawing muna natin yung ating schematic diagram. We know that we have a refrigerator, and we know that in a refrigerator, the goal is for it to absorb heat from a low temperature reservoir. So here, Q dot C is just equal to 2 kilowatts, and ang ating low temperature reservoir, TC, ay nasa temperature na negative 30 degrees Celsius. We also know that it rejects heat at a high temperature reservoir. At according sa ating problem, ang temperature ng ating high temperature reservoir, TH, is equal to 20 degrees Celsius because our household freezer is inside a room at 20 degrees Celsius. Hindi given ang QH or Q.H, so this is one of the unknowns in our problem. And finally, the one that we're looking for is W.in, provided na ang ating refrigerator ay tumatakbo based on the theoretically smallest power input. So we are looking for W.in minimum. Now, we can argue na ang minimum power input W.in minimum ay makukuha at the most efficient refrigerator that we have. So let me just write it down. At the most quote-unquote efficient refrigerator, then we can get the minimum power input that is theoretically possible. This happens kung ang ating coefficient of performance beta is at maximum. According to the definition of the Kelvin temperature scale, we have concluded that the maximum coefficient of performance beta max is given by the formula Tc all over Th minus Tc. Whereas all the temperatures that we have here are all in Kelvin temperature. So ang pwede natin gawin dito ay isolve natin si beta max dahil we can actually obtain that because of the fact that the temperatures Tc and Th are already given over here. And in our formula, since sinabi natin kailangan sila ay naka-Kelvin temperature, we have to convert these temperatures first. Let us do so. We have negative 30 degrees Celsius plus 273.15. That will give us a temperature of 243.15 Kelvin. That is for TC. And finally, for TH, we have 20 degrees Celsius plus 273.15, and that gives us 293.15 Kelvin. Take note that whatever Betamax that we can obtain using this formula, that is formula A, can be equated to Q dot C, which is basically the cooling effect inside the refrigerator, divided by the power input in our refrigerator. And take note that this power input is minimum because the coefficient of performance is maximum, theoretically maximum. So let's call this formula A and this one formula B. Now, using formula A, let's obtain the maximum coefficient of performance beta max. We have TC, which is 243.15 Kelvin, divided by TH, which is 293.15 Kelvin, minus TC. Substituting these values in our calculator, we have the following. So the maximum coefficient of performance, beta max, for this particular refrigerator at these operating temperatures is 4.863. Let me just write that down. As I have mentioned, ang pwede natin gawin susunod ay palitan itong beta max na ito ng 4.863. And of course, this QC over here, with the rate of cooling that is equal to 2 kilowatts. Transforming this formula, we have the minimum power input, that's just going to be equal to 2 kilowatts, divided by 4.863. Substituting these values in our calculator, we have the following. 2 divided by whatever the answer that we got a while ago. The minimum power input, therefore, is 0.4113 kilowatts. Let me just write it down. Now, let's move forward to the second problem in this lecture video before we end the session. A cyclic machine, shown in the figure below, receives 325 kilojoules from a 1000 Kelvin energy reservoir. It rejects 125 kilojoules to a 400 Kelvin energy reservoir, and the cycle produces 200 kilojoules of work as output. Is this cycle reversible, irreversible, or impossible? Nakasulat na dito ang mga given sa ating problem. We have heat absorption at 1000 Kelvin. So they already gave the temperatures in terms of Kelvin. We have QL over here that is equal to 125 and the power output at 200 kilojoules. So kapag meron tayong mga problems kung saan pinapatukoy sa atin kung implementable ba ang ating thermodynamic system, ang una muna natin gagawin ay i-check muna siya using the first law of thermodynamics. Kung ang ating thermodynamic cycle ay nag-violate ng first law of thermodynamics, then pwede na natin sabihin as early as now na impossible ang ating system. However, in any case na pumasa siya sa first law of thermodynamics, then we have to check first if pasado din ba siya sa second law of thermodynamics. So first, we inspect our system using the first law of thermodynamics. Alam natin na sa isang thermodynamic cycle, lahat ng energies na pumapasok ay lumalabas lang din. So we have energy in is equal to energy out. And upon inspection, makikita natin ang tanging pumapasok na energy sa ating system ay QH. So we have QH equals to all the energies that are going out, which are the work output and the heat rejection at the low temperature reservoir. So we have QH that is equal to W plus QL. Now, let us substitute the numbers that we have. We have 325 kilojoules. The question is it equal to 200 kilojoules plus 125 kilojoules? And without even using the calculator, you can conclude that they are indeed equal to each other. Therefore, it passes the first law of thermodynamics. However, this is still inconclusive as of the moment dahil kailangan pa natin siyang i-check using the second law of thermodynamics. More specifically, we can use the definition of the Kelvin temperature in order to determine the maximum efficiency of our heat engine. So we first need to solve for eta max, the maximum efficiency of our cyclic machine, and compare it with the actual efficiency of our machine. Of course, kung ang ating actual efficiency ay mas mababa sa ating maximum efficiency, then we say that our process is irreversible. If the maximum efficiency is equal to the actual efficiency, then masasabi natin na ang ating cyclic machine ay nag-undergo ng isang reversible cycle. However, if the actual efficiency is higher than the maximum efficiency, logically and thermodynamically, the cycle by which the cyclic machine is operating is impossible. Now, recall that the formula for the maximum efficiency of a heat engine is just given by 1 minus TL over TH. Also, recall na ang actual efficiency ng ating heat engine ay equal lang sa 1 minus QL over QH. Substituting the numbers that we know, alam natin na si TL ay equal lang sa 400 Kelvin at ang TH ay equal lang sa 1000 Kelvin. So we have 1 minus 400 over 1000. Therefore, we have eta max that is equal to the following. That is the maximum efficiency of around 60%. Let me just write that down. Now, let us compare it with the actual efficiency of the machine. So we have eta actual, that is 1 minus QL, where QL is equal to 125 kilojoules, divided by QH, where QH is equal to 325 kilojoules. Our actual efficiency for this machine is just equal to the following. We have around 61.54%. So, makikita natin dito na ang ating efficiency, actual efficiency more specifically, is larger than the maximum efficiency. This means that our cyclic machine is impossible to implement. That's it for this video. I hope you learned something and see you in the next videos.